Tonight, we're going to explore something that shouldn't be possible, according to basic logic. The universe is packed with stars, an almost incomprehensible number of them, and every single one of them radiates light, constantly, without fail. Multiply that light by every star in every galaxy, and the math says the entire sky, in every direction, should be burning bright. Instead, the night sky is mostly dark. And that darkness doesn't stop at the edge of what you can see. It extends outward, through the space between stars, between galaxies, filling nearly the entire universe with an emptiness far darker than anything visible from Earth. By the end of tonight, you're going to understand the real reason behind that contradiction, and how it connects directly to the age, size, and history of the universe itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Look up on a clear night. Far from city lights, you'll see stars scattered across the darkness. Thousands of them, if your eyes are sharp and the sky is clear enough. Each one is a sun, pouring out light in every direction, constantly, relentlessly, for billions of years. And yet, between those points of light, there's nothing but black. Vast stretches of empty darkness separating one glowing point from the next. At first glance, this seems obvious. Of course, space is dark. Stars are far apart, and the space between them is empty. But that simple explanation doesn't hold up once you start thinking carefully about the math. Here's the problem. The universe contains an enormous number of stars. Our galaxy alone, the Milky Way, contains somewhere between 100 billion and 400 billion stars. And our galaxy is just one among an estimated 2 trillion galaxies in the observable universe. Multiply those numbers together, and you get a number of stars so large it becomes difficult to even comprehend. Something in the range of 1 septillion stars, a 1 followed by 24 zeros, scattered across the observable universe. Now, here's where it gets strange. Imagine standing at any point in an infinite universe filled with stars. Look in any direction, and your line of sight should eventually hit a star. Think of it like standing in an enormous forest. If the forest is large enough, no matter which direction you look, eventually your line of sight will hit a tree trunk. You won't be able to see all the way to the horizon because trees will block your view in every direction. The same logic applies to stars. If the universe is infinite, or even just extremely large, and filled evenly with stars, every single line of sight from Earth should eventually terminate on the surface of a star. Every point in the sky should be as bright as the surface of a star. The entire sky, day and night, should be blazing with light. This isn't some fringe idea. It's a straightforward consequence of geometry and the assumption that the universe is infinite, unchanging, and uniformly filled with stars. And yet, when we look up, we see mostly darkness with scattered points of light. This contradiction has a name. It's called Olbers Paradox, named after the German astronomer Heinrich Wilhelm Olbers, who wrote about it extensively in 1823. Though, as with many famous scientific puzzles, Olbers wasn't actually the first person to notice it. The roots of this puzzle stretch back further than you might expect. As early as the 16th century, The English astronomer Thomas Digges proposed that stars extend infinitely into space. Digges was one of the first supporters of the Copernican idea that the Sun, not the Earth, sits at the center of the solar system. He imagined a universe without boundaries, filled endlessly with stars. But if that were true, shouldn't the night sky be uniformly bright? Digges didn't fully grapple with the implications, but the seed of the paradox was planted. In the following centuries, astronomers and philosophers returned to this puzzle again and again. Johannes Kepler, the brilliant astronomer who described the laws of planetary motion in the early 1600s, actually used the darkness of the night sky as an argument against an infinite universe. Kepler reasoned that if the universe were truly infinite and filled with stars, the sky would be a wall of light. Since it clearly wasn't, he concluded the universe must be finite, bounded by some kind of edge or shell beyond which there were no more stars. It was a reasonable conclusion given what was known at the time, but it wasn't quite right either, as we'll see. The paradox resurfaced repeatedly over the following 2 centuries. The astronomer Edmund Halley, famous for the comet that bears his name, wrote about the puzzle in the early 1700s. Halley actually agreed with Digges, arguing that the universe truly was infinite, but that starlight from the most distant stars simply became too faint to see at all. But this explanation didn't hold up under scrutiny either, because fainter light from more distant stars is still light, and Olbers would later show mathematically that the growing number of stars at greater distances exactly compensates for their fainter individual brightness. The Swiss astronomer Jean-Philippe Loys de Chezeaux examined the problem mathematically in 1744. He proposed one of the first serious attempts at a solution, suggesting that light might be absorbed or dimmed as it traveled across immense distances, perhaps by some kind of medium filling the space between stars. It was a clever idea, and it would resurface again decades later, but it carried within it a flaw that wouldn't become obvious until physicists understood more about how energy and heat actually work. But it was Heinrich Olbers who, in 1823, presented the puzzle so clearly and forcefully that it became permanently associated with his name. Olbers approached the problem with careful mathematical reasoning. He pointed out that even though stars appear dimmer the farther away they are, that dimming is exactly compensated for by the fact that there are more stars at greater distances. Think about it this way. If you double the distance to a star, its apparent brightness drops to 1/4, because brightness falls off with the square of distance. But imagine a spherical shell of space at that doubled distance. The volume of that shell, and therefore the number of stars contained within it, increases with the square of the distance as well. The two effects cancel out perfectly. Each shell of stars at increasing distance contributes the same total amount of light to the sky as every other shell. Add up an infinite number of shells and you get infinite brightness. The entire sky should glow like the surface of the sun. Olbers' math was correct. His logic was sound. And yet reality clearly disagreed with him. This is what makes a good paradox. Not a mistake in reasoning, but a case where careful, logical thinking leads to a conclusion that clearly contradicts what we observe. Something in the assumptions had to be wrong. For much of the 19th century, this remained an open and genuinely puzzling question. Some astronomers proposed that interstellar dust and gas absorbed the light from distant stars, dimming them before they reached us. This seemed like a reasonable explanation at first, and it echoed de Chazot's earlier suggestion. But there was a fatal flaw. If dust absorbs light, that dust itself heats up. Given enough time, an infinite amount of time in fact, that dust would eventually radiate as much energy as it absorbed. It would glow just as brightly as the stars behind it. Absorption alone couldn't solve the paradox. It could only delay the problem, not eliminate it. Physicists in the late 1800s and early 1900s understood this through a principle called thermal equilibrium. Any object that absorbs radiation will, given sufficient time, reach the same temperature as the source of that radiation. Once it reaches that temperature, it radiates just as much energy as it takes in. A cloud of interstellar dust sitting in an infinite, unchanging universe filled with starlight from every direction would eventually heat up to match the temperature of a stellar surface somewhere in the range of thousands of degrees. It would then glow just as brightly as the stars it was supposedly blocking. So dust and gas, while they do dim and redden starlight in the real universe we live in, cannot be the fundamental solution to Olbers' paradox. The true resolution wouldn't come until the 20th century, and it required physicists and astronomers to fundamentally rethink what the universe actually is. The first crucial piece of the puzzle is something you might already suspect. The universe is not infinitely old. For most of human history, and even through much of the 19th century, many scientists assumed the universe had simply always existed. Unchanging, eternal, stretching backward and forward in time without limit. This was called the steady-state view, and it wasn't a fringe idea. It was the dominant assumption among scientists for a very long time, partly because it seemed philosophically cleaner, and partly because there was no observational evidence pointing clearly in any other direction. If the universe had always existed exactly as it appears now, there would have been enough time, an infinite amount of time, in fact, for light from every star in an infinite universe to reach every point in space. That would fill the sky with light exactly as Olbers calculated. But we now know the universe is not eternal. It had a beginning. According to the best current measurements, the universe came into existence approximately 13.8 billion years ago in an event we call the Big Bang. Before that moment, space and time, as we understand them, did not exist in their current form. This changes everything about the paradox. Light travels at a finite speed, about 186,000 miles per second. That sounds incredibly fast, and it is. But the universe is so vast that light takes a very long time to cross it. Because the universe is only 13.8 billion years old, we can only see light that has had time to reach us since the beginning of the universe. This creates something astronomers call the observable universe, a boundary beyond which we simply cannot see. Not because there's nothing there, but because light from beyond that boundary hasn't had enough time to reach Earth yet. Think of it like this. If you turn on a flashlight in a completely dark room, the light doesn't fill the entire room instantaneously. It takes a tiny fraction of a second to travel outward and illuminate the walls. In an infinite room, no matter how long you left the flashlight on, if the room truly stretched forever, there would still be regions the light hadn't reached yet. That's because you can't propagate information or energy faster than light speed. The universe works the same way. just on a mind-bending scale. Stars and galaxies exist far beyond what we can currently observe. But their light hasn't reached us yet, and in many cases, it never will, for reasons we'll get to shortly. This alone solves a significant part of Olbers Paradox. The sky isn't infinitely bright because the universe isn't infinitely old, and therefore we can't see infinitely far. We can only see a finite number of stars, those within our cosmic light horizon, not an infinite number. The idea of a finite expanding universe with an actual beginning wasn't seriously proposed until the 20th century, and even then it faced enormous resistance. Many scientists, including some of the most respected minds of the era, found the idea of a universe with a beginning philosophically uncomfortable. It suggested that there was a moment before which the normal laws of cause and effect, the very fabric of space and time, simply didn't apply in the way we understand them. But the evidence for a beginning kept accumulating, and eventually it became undeniable. Even accounting for the finite age of the universe, when astronomers ran the numbers, they found that the observable universe still contains an absolutely staggering number of stars. More than enough, in theory, to fill the sky with light many times over if they were all shining directly toward us, with nothing standing in the way. So there had to be more to the explanation. The second crucial piece of the puzzle involves something almost nobody expected in the 1800s. The universe is expanding. This discovery came in the late 1920s when the American astronomer Edwin Hubble made a series of careful observations of distant galaxies. He used the largest telescope in the world at the time, perched on top of Mount Wilson in California. Hubble was measuring what astronomers call redshift, a subtle change in the color of light coming from distant objects. He compared it to the distances of those objects, which he calculated using a special class of stars called Cepheid variables. Stars whose brightness pulses in a predictable way that lets astronomers use them as reliable distance markers. What Hubble discovered was remarkable. Nearly every galaxy he observed was moving away from us. And the farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, was completely unexpected. Before this, most astronomers, including Albert Einstein himself, assumed the universe was static, neither expanding nor contracting, simply existing in a fixed, unchanging state. Einstein had even added a term to his own equations of general relativity, something he called the cosmological constant, specifically to force his mathematical model of the universe to remain static. The raw equations kept predicting an expanding or contracting universe, and that seemed absurd to him at the time. When Hubble's observations came in, showing that galaxies really were rushing away from us, Einstein reportedly called the cosmological constant his greatest blunder. Though the story of exactly what he said and when has become somewhat exaggerated over the years. The discovery of cosmic expansion wasn't a matter of galaxies flying through static space like bullets fired from a gun. That's an important distinction. Space itself was stretching, expanding, carrying galaxies apart from one another as it grew. Think of raisins in a rising loaf of bread, moving apart from each other as the dough itself expands. Not because the raisins are moving through the dough, but because the dough between them is growing. This discovery fundamentally transformed our understanding of the cosmos. The universe wasn't a fixed, eternal stage upon which stars simply existed. It was dynamic, evolving, expanding outward from an incredibly hot, dense state in the distant past. Run the expansion backward in time, mathematically, and all the galaxies converge toward a single point, an extraordinarily hot and dense state that existed roughly 13.8 billion years ago. This is what we now call the Big Bang, and it wasn't an explosion happening at a point within space, the way people sometimes imagine it. It was the beginning of space and time themselves, everywhere at once, followed by relentless expansion ever since. This expansion has a critical consequence for light. As light travels across the expanding universe, the space it's traveling through stretches, and that stretching increases the wavelength of the light itself. This effect is called redshift, because stretching a light wave shifts it toward the longer, redder end of the visible spectrum. Imagine drawing a wave pattern on a rubber band, then stretching that rubber band. The peaks and troughs of the wave get pulled farther apart, meaning the wavelength increases. That's essentially what happens to light traveling through expanding space, except instead of a rubber band, it's the fabric of space itself doing the stretching. The farther light has traveled, and the more space has expanded during that journey, the more its wavelength gets stretched. For light from very distant galaxies whose light left billions of years ago, the redshift is extreme. Visible light gets stretched all the way into infrared, and then into microwave wavelengths, completely invisible to the human eye. This is enormously important for understanding the darkness of the night sky. Even stars and galaxies whose light theoretically reaches us are being systematically dimmed and shifted out of the visible spectrum by the ongoing expansion of space itself. Their energy isn't gone. It's just been stretched into wavelengths our eyes simply cannot detect. There's also a more subtle effect at play. As space expands, the energy carried by each individual photon of light actually decreases. A photon's energy is directly tied to its wavelength. Shorter wavelengths carry more energy, longer wavelengths carry less. This relationship comes directly from quantum mechanics, described by the equation E equals h times f. Here, E is energy. H is a fundamental constant called Planck's constant, and f is the frequency of the light. Since frequency and wavelength are inversely related, stretching the wavelength lowers the frequency, and lowering the frequency lowers the energy. When the expansion of the universe stretches a photon's wavelength, it literally reduces the amount of energy that photon carries. This means that ancient light arriving from the deep universe isn't just shifted in color. It's genuinely weaker, carrying less energy than it did when it was first emitted. Combine this with the finite age of the universe, and you start to see how the sky could remain mostly dark despite containing so many stars. We can only see light from a finite volume of space, the observable universe, and much of that light has been redshifted and weakened by cosmic expansion, to the point where it contributes very little to what we perceive as visible brightness. Not every star and galaxy we can technically see is contributing equally to the darkness or brightness of our sky. Nearby stars, the ones within our own galaxy, haven't had their light meaningfully redshifted at all. The distances involved are small enough, and the timescales short enough that cosmic expansion barely factors in over those distances. That's why the stars you see with your naked eye still appear as sharp, bright points of white or slightly colored light, not stretched into invisible infrared. But once you start looking at galaxies millions and billions of light years away, redshift becomes an enormous factor. By the time you're looking at the most distant galaxies we can detect, whose light has been traveling for over 13 billion years, that light has been redshifted so dramatically that it's no longer visible light at all by the time it reaches our telescopes. This is why the most powerful instruments we've built for studying the deep universe, telescopes like the James Webb Space Telescope, are designed specifically to observe in infrared wavelengths. They're built to catch the redshifted light of the earliest galaxies, light that started out as visible or even ultraviolet radiation billions of years ago, but has been stretched by cosmic expansion into the infrared by the time it reaches us. But there's a third factor that completes the picture, one that's arguably the most intuitive of all, once you think about it carefully. Stars, even though there are enormous numbers of them, occupy an infinitesimally small fraction of the sky. Consider the actual physical size of stars compared to the vast distances between them. Our Sun, an average-sized star, has a diameter of about 865,000 miles. That sounds enormous, and by human standards, it is. You could fit over 1 million Earths inside a sphere the size of the Sun. But the nearest star system to our own, Alpha Centauri, sits about 4.24 light-years away, a distance of roughly 25 trillion miles. If you were to scale the Sun down to the size of a grain of sand, the nearest star, on that same scale, would be a different grain of sand, located many miles away. Nearly all of that intervening distance is empty space. This ratio, the physical size of a star compared to the distance separating it from its neighbors, is what astronomers describe using the concept of angular size. Essentially, how large an object appears in the sky based on both its actual size and its distance from the observer. Even though stars are physically enormous compared to a human being, their angular size, as seen from Earth, is almost unimaginably tiny, because the distances involved are so much larger still. The Sun, viewed from Earth, appears as a disk about half a degree wide in the sky. That sounds substantial, but it's only because the Sun is relatively close to us, roughly 93 million miles away, a distance that's almost nothing on cosmic scales. Move that same star out to the distance of Alpha Centauri, and its angular size shrinks to a point so small it becomes indistinguishable from a single point of light, even through powerful telescopes. This means that even though there might be an enormous number of stars scattered throughout the observable universe, each individual star occupies such a tiny, angular size in our sky. The odds of any particular line of sight actually intersecting the visible surface of a star, rather than passing through the empty space around it, are astronomically small. Remember the forest analogy from earlier, where every line of sight eventually hits a tree trunk if the forest is large enough. That analogy assumed the forest was infinite, or at least large enough relative to the size of the trees for that geometric certainty to hold. But our observable universe, despite its staggering scale, is not infinite. It's finite, bounded by the age of the universe and the speed of light. And within that finite volume, 10 to the 1, stars are so small and so sparsely distributed relative to the size of the space they occupy that the vast majority of lines of sight from Earth pass through nothing but empty space. or through gas and dust, too tenuous and too cold to glow visibly, before reaching the very edge of what we can observe. Only a relatively small fraction of all possible directions in the sky actually terminate on the visible disk of a star. The rest stretch out into darkness, either because there's genuinely nothing there within the observable limit, or because whatever light exists along that path has been so redshifted and weakened by cosmic expansion that it no longer registers as visible light to our eyes. If you could somehow calculate the actual fraction of the sky covered by the visible disks of all the stars within our observable universe, it would come out to an almost unbelievably small number. Far less than 1 part in many trillions. Space, quite literally, is mostly empty space. Even when you account for every single star that has ever formed within the boundaries of what we can observe. Put these 3 factors together: the finite age of the universe, the expansion of space, and the resulting redshift and energy loss of ancient light, and the sheer physical smallness of stars relative to the distances separating them. Olbers Paradox dissolves entirely. The night sky is dark, not because there aren't enough stars. There certainly are enough, in the sheer statistical sense Olbers imagined. It's dark because the universe has a beginning, and because light takes time to travel. It's dark because space itself has been stretching and diluting the energy of ancient starlight for billions of years. And it's dark because stars, despite their brilliance, are staggeringly small points scattered across an almost incomprehensibly vast volume of space. The darkness of the sky connects directly to the very origin of the universe itself, through one of the most famous accidental discoveries in the history of science. While the visible sky appears dark, it isn't actually empty of light in every wavelength. In the 1960s, 2 radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey. They were using a large horn-shaped antenna originally built for satellite communication experiments. They wanted to repurpose it for radio astronomy, to study faint radio signals from the Milky Way. But every time they pointed the antenna at the sky, no matter which direction, they kept picking up a faint, persistent hiss of microwave radiation. At first, they assumed it was some kind of equipment malfunction. They checked every possible source of interference. They considered nearby New York City, radar installations, even nuclear testing that had occurred years earlier. They cleaned the antenna thoroughly, and famously, they even removed pigeon droppings from the equipment. A pair of pigeons had been nesting inside the horn, and they thought that might be the source of the noise. Nothing worked. The signal remained constant, uniform, coming equally from every direction in the sky, day and night, regardless of the season. Meanwhile, completely unaware of what Penzias and Wilson were finding, a team of physicists at nearby Princeton University, led by Robert Dick, had been working on a theoretical prediction. If the Big Bang theory were correct, they reasoned, there should be a faint, uniform glow of radiation left over from the early universe, now cooled down to just a few degrees above absolute zero due to billions of years of cosmic expansion. When the 2 teams learned of each other's work, the pieces fell into place immediately. What Penzias and Wilson had accidentally discovered was the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This radiation is essentially the oldest light in the universe, released about 380,000 years after the Big Bang. That's when the universe had finally cooled enough for electrons and protons to combine into neutral hydrogen atoms, in an event cosmologists call recombination. Before that moment, the universe was filled with a hot, dense plasma of charged particles, and light couldn't travel freely through it. It kept scattering off free electrons, the way light scatters through a thick fog. Once neutral atoms formed, the universe suddenly became transparent, and light was able to travel freely through space for the very first time. That light, released in every direction throughout the universe at that moment, is what we now detect as the cosmic microwave background. At the moment this light was released, it was extraordinarily hot and energetic, similar to the light emitted by a glowing object with a temperature of nearly 5,000 degrees Fahrenheit, or about 2,760 degrees Celsius. Roughly, the color of the surface of a star. But that light has been traveling through an expanding universe for nearly 14 billion years. During that immense journey, the relentless stretching of space has redshifted this ancient light dramatically, transforming it from visible light into microwave radiation. It now corresponds to a temperature of just a few degrees above absolute zero, about negative 455 degrees Fahrenheit, or about negative 270 degrees Celsius. This is a beautiful and direct confirmation of everything we've discussed. The universe was once filled with intensely bright light, hot enough and dense enough to fill every direction in the sky the way Olbers imagined. But billions of years of cosmic expansion have stretched and cooled that primordial light so dramatically that it no longer appears as visible brightness at all. It appears instead as a faint, uniform microwave hiss, completely invisible to human eyes, detectable only with specialized radio telescopes. In a very real sense, the entire sky actually is glowing, exactly as Olbers predicted, just not in the way anyone in the 1800s could have imagined. The glow is there. It's just been stretched so far beyond the visible spectrum by the expansion of the universe that our eyes simply cannot perceive it. If human eyes could somehow see in microwave wavelengths, the entire sky, every single direction you looked, would appear to glow with an almost perfectly uniform faint light. The leftover heat of creation itself, still detectable after nearly 14 billion years. This discovery earned Penzias and Wilson the Nobel Prize in Physics in 1978, and it remains one of the strongest pieces of observational evidence supporting the Big Bang theory. It also stands as a remarkable example of how science sometimes advances. Not through a carefully planned experiment designed to test a specific hypothesis, but through careful, honest observation of something unexpected, followed by the humility to admit that a strange signal might be telling you something profound about the universe, rather than simply being noise to be eliminated. This background radiation has become one of the most precisely measured signals in all of science since its initial discovery, and the instruments built to study it have grown more sensitive with almost every passing decade. In the decades since Penzias and Wilson's accidental find, scientists have launched increasingly sophisticated instruments specifically designed to map this cosmic microwave background in exquisite detail. The Cosmic Background Explorer satellite, launched in 1989, confirmed that this radiation follows an almost perfect blackbody spectrum. Exactly what you'd expect from thermal radiation left over from an extremely hot, dense, early universe. Later missions, the Wilkinson Microwave Anisotropy Probe, launched in 2001, and the Planck Satellite, launched in 2009, mapped tiny temperature variations in this background radiation with extraordinary precision. Variations of just a few parts in 100,000. These tiny fluctuations might seem insignificant, but they represent the seeds of all the structure we see in today's universe. The slightly denser regions of the early universe that would eventually collapse under their own gravity to form the first stars, the first galaxies, and eventually the vast cosmic web of galaxy clusters and filaments that stretches across the observable universe today. In a strange and beautiful way, this connects directly back to our original question about why the sky is dark. The tiny imperfections in that ancient, now invisible glow are the reason stars exist at all. Without those slight variations in density, matter would have remained perfectly smooth and evenly distributed throughout the universe. Gravity would have had nothing to grab onto, no denser regions to pull matter toward, no seeds around which stars and galaxies could form. The universe would have remained a thin, uniform soup of gas forever, with no stars, no galaxies, and, quite literally, nothing to look at when you glanced up at what would have been an eternally, perfectly dark sky. So the very darkness we're trying to explain, and the tiny, hidden imperfections buried within the leftover light of the Big Bang, are intimately connected. The universe needed those imperfections to create stars in the first place, and it's the finite, expanding nature of that same universe that ensures those stars don't fill the entire sky with light. Beyond stars themselves, the broader, large-scale structure of the cosmos plays a role in this puzzle too. Galaxies aren't scattered randomly and uniformly throughout space. They're organized into an enormous, intricate structure that astronomers call the cosmic web. Picture an enormous three-dimensional network of filaments, sheets, and clusters of galaxies, separated by vast, nearly empty regions called cosmic voids. Galaxies tend to cluster along these filaments, drawn together by gravity over billions of years. The voids between them remain relatively empty, containing far fewer galaxies, far fewer stars, and correspondingly, far less light. Some of these cosmic voids are staggeringly large, hundreds of millions of light-years across, regions of space containing only a small fraction of the galaxies you'd expect if matter were evenly distributed throughout the universe. If you happen to be located near the center of one of these enormous voids, looking out into the surrounding darkness, an even larger fraction of your sky would appear empty and black. There are simply dramatically fewer galaxies, and therefore dramatically fewer stars, along most lines of sight in any direction. Fortunately, or perhaps just as a matter of cosmic circumstance, our own galaxy sits within a moderately dense region of the cosmic web. Part of a structure astronomers call the local group, which itself is part of a larger structure called the Laniakea supercluster. But even from our relatively well-populated cosmic neighborhood, the fundamental principles we've discussed still apply. The universe is finite in the sense that matter's here, bounded by its age and the speed of light. Expansion is constantly redshifting and weakening the light of distant objects, and individual stars remain infinitesimally small points scattered across enormous distances. This uneven, clustered distribution of matter throughout the universe adds yet another layer of texture to why the sky looks the way it does. Dense bands of stars along the plane of our own galaxy, visible as the hazy band we call the Milky Way when we look up on a truly dark night, and comparatively sparser regions elsewhere, where individual galaxies appear only as faint, barely visible smudges, if they're visible to the naked eye at all. There's a biological piece of this puzzle too, one that has nothing to do with astrophysics and everything to do with the way human eyes actually work. Even if the universe was somehow arranged to send far more starlight toward Earth than it currently does, there are real limits to how bright a scattering of individual, distant points of light can appear to a human observer, especially at night, when the eye is operating in a completely different mode than it does during the day. Human eyes contain two types of light-sensitive cells, rods and cones. Cones are responsible for color, vision, and detailed sight in bright conditions, while rods are far more sensitive to low light, but cannot distinguish color and provide much lower resolution. At night, in genuinely dark conditions, your eyes shift almost entirely to relying on rod cells. This transition, called dark adaptation, can take up to 30 minutes to fully complete. This is why your night vision keeps improving the longer you stay outside in the dark, away from any bright lights. But even fully adapted rod vision has limits. Each rod cell can technically detect a single photon of light under ideal laboratory conditions, an extraordinary level of sensitivity. However, individual stars, even bright ones, deliver only a relatively small trickle of photons to your eye, spread out over time. Your brain needs to integrate signals from multiple rod cells over a short window of time to register something as a distinct point of light rather than random background noise. This is part of why very faint, distant stars remain invisible to the naked eye, even on the clearest, darkest nights. Not because there's no light reaching your eye at all, but because the amount of light is simply too sparse, too infrequent, for your visual system to reliably distinguish it from nothing. Telescopes solve this problem in two ways. First, they gather far more light than the tiny pupil of a human eye ever could. They use large mirrors or lenses to collect photons across a much greater surface area, effectively acting like a much bigger, more light-hungry eye. Second, modern astronomical instruments can integrate, or add up, incoming light over long exposure times, sometimes hours or even days. This allows extraordinarily faint objects, galaxies whose combined light would be utterly invisible to a human eye in a single instant, to gradually build up into a clear, detailed image on a sensor. This is exactly how images like the famous Hubble Deep Field were created. Astronomers pointed the Hubble Space Telescope at what appeared to be a completely empty, dark patch of sky, seemingly devoid of any stars or galaxies at all, and left the camera shutter open for a cumulative exposure time of many hours across multiple observing sessions. What emerged was staggering. That seemingly empty patch of sky, a region so small it could be covered by a grain of sand held at arm's length, turned out to contain thousands of individual galaxies. Each one containing billions of stars, all invisible to the naked eye, and all invisible even to a single short exposure through a telescope, but revealed gradually as photons accumulated over time. This tells us something important about the darkness we perceive with our own eyes. A significant amount of the darkness in the night sky isn't necessarily because there's genuinely nothing there. Some of it is simply because human vision even under the best conditions, has limits. Countless faint galaxies exist in every direction, contributing an almost immeasurably small trickle of light that our eyes simply cannot detect without technological assistance. But this observation, while fascinating, doesn't undermine the resolution to Olbers Paradox that we discussed earlier. Even accounting for the existence of these countless faint, distant galaxies invisible to human eyes, the total combined light reaching Earth from the observable universe still falls dramatically short of filling the sky with uniform brightness. That's precisely because of the finite age of the universe, the redshifting effects of cosmic expansion, and the enormous distances involved. The Hubble Deep Field reveals thousands of galaxies in what looks like an empty patch of sky, but it doesn't reveal an infinite number of galaxies. And even that image, remarkable as it is, still shows a background that's overwhelmingly, fundamentally black, dotted with points and smudges of light, rather than filled uniformly with brightness. There's another layer of darkness in the universe beyond what we've already covered, and it has nothing to do with stars at all. Ordinary matter, the atoms that make up stars, planets, and everything you can directly see or touch, actually makes up only a small fraction of the total mass and energy content of the universe. Based on decades of careful astronomical observation, including the precise measurements of the cosmic microwave background we discussed earlier, cosmologists have determined that ordinary matter accounts for only about 5% of the universe's total energy content. Roughly 27% is something called dark matter, a mysterious form of matter that doesn't emit, absorb, or reflect light at all. It can currently only be detected indirectly through its gravitational influence on visible matter, on the rotation of galaxies, and on the bending of light around massive cosmic structures, an effect called gravitational lensing. The remaining 68% is something even stranger, called dark energy, a mysterious force or property of space itself that appears to be responsible for the accelerating expansion of the universe that astronomers discovered in the late 1990s. Neither dark matter nor dark energy interacts with light the way ordinary matter does. They don't glow. They don't block light in any conventional sense. They're simply, by their very nature, invisible, detectable only through their gravitational and cosmological effects, rather than through any kind of direct observation. This means that the vast majority of the universe, in terms of its actual mass and energy content, wouldn't contribute to sky brightness, even in a hypothetical version of Olbers' scenario, where the universe was infinitely old and completely filled with visible matter. Only ordinary, luminous matter, the roughly 5% of the universe made of atoms capable of forming stars that shine, would ever contribute light to the night sky in the first place. The other 95% of everything that exists is, in a very real sense, permanently dark, regardless of any of the other factors we've discussed. This adds a strange and somewhat humbling dimension to our original question. Not only is the sky dark because of the age of the universe, the expansion of space, and the small angular size of stars relative to the distances between them. The overwhelming majority of what actually exists throughout the cosmos wouldn't glow even under the most generous hypothetical conditions, because it isn't made of the kind of matter capable of producing light through nuclear fusion or any other radiative process we currently understand. We are, in the most literal sense, living in a universe where visible light, the kind of light that lets us see stars, galaxies, and everything else we can observe with telescopes, represents only a small sliver of everything that actually exists. There's a question that naturally follows from everything we've covered so far, and it's one that takes us into deep future. If the darkness of the sky is a consequence of the universe's youth, relatively speaking, on cosmic timescales, what happens as the universe continues to age? We've already touched on this briefly, but it deserves a closer look, because the answer reveals something almost melancholic about the long-term fate of the cosmos. Right now, we happen to exist during what astronomers sometimes call the stelliferous era, a period in cosmic history defined by active star formation. Stars are being born constantly throughout the universe, condensing out of vast clouds of hydrogen and helium gas within galaxies, ignited by the immense pressure and temperature generated as gravity pulls that gas together until nuclear fusion begins in the core. Our own galaxy, the Milky Way, forms new stars at a rate of roughly 1 to 2 solar masses worth of material per year. This process isn't spread evenly, though. It's concentrated in specific regions, particularly along the spiral arms, where dense clouds of gas and dust provide the raw materials stars need. This ongoing star formation is part of why the night sky, dark as it fundamentally is according to everything we've discussed, still contains countless visible points of light. New stars are constantly being added to the population, replacing older stars as they exhaust their nuclear fuel and evolve into different phases. Some expand into red giants. Some end their lives in dramatic supernova explosions. Some quietly fade into dense remnants called white dwarfs, neutron stars, or in the most extreme cases, black holes. But this process cannot continue forever. Star formation depends on a continuous supply of hydrogen gas. The universe currently contains enormous reserves of this raw material, but that supply is finite, and it's being steadily consumed. Astronomers estimate that active star formation throughout the universe will continue for an extraordinarily long time by human standards, but it isn't infinite. Current models suggest that meaningful star formation will continue for perhaps another 100 trillion years, though it will become increasingly sparse and infrequent as usable hydrogen gas becomes harder and harder to find in sufficient concentrations. After that point, the universe will enter what's sometimes called the degenerate era. This is a period potentially lasting from 100 trillion years to as long as 10 to the power of 40 years, an almost incomprehensibly long stretch of cosmic time, during which the universe will be populated primarily by the dim, cooling remnants of stars that have already exhausted their fuel. White dwarfs, the collapsed cores, left behind by stars similar in mass to our own sun, will slowly cool over unimaginable timescales. They'll fade from a dull red glow to eventual, nearly complete darkness, becoming what physicists call black dwarfs. Though no black dwarf actually exists yet in our current universe, because the process of cooling to that point takes far longer than the current age of the universe itself. Neutron stars, the incredibly dense remnants left behind by more massive stars, will similarly cool and fade over vast stretches of time. Black holes, meanwhile, will continue to exist for far longer still, but they too are not truly eternal. According to theoretical physics developed in the 1970s, primarily through the work of physicist Stephen Hawking, Black holes slowly lose mass over time through a process called Hawking radiation. This is an extraordinarily slow leakage of particles that eventually causes even the largest black holes to evaporate entirely. Though this process takes a length of time so vast, it dwarfs every other timescale we've discussed. Potentially 10 to the power of 100 years or more for the largest supermassive black holes. Layered on top of all of this stellar evolution is the relentless expansion of the universe itself. As we discussed earlier, that expansion is not just continuing, but actually accelerating, driven by dark energy. As expansion continues and accelerates, distant galaxies will be carried away from us at ever-increasing rates. Eventually, they'll cross a boundary called the cosmological event horizon, beyond which their light, no matter how long we wait, will never be able to reach us again. Galaxies currently visible in our night sky, galaxies whose light we can detect today with powerful telescopes, will gradually vanish from our observable universe as expansion carries them beyond this horizon. This won't happen quickly on human timescales. It's a process spanning tens of billions to hundreds of billions of years, but it's happening continuously, right now, as you listen to this. Eventually, in an almost inconceivably distant future, our own galaxy will merge with its nearby neighbors, including the Andromeda Galaxy, in a slow gravitational dance that will unfold over the next several billion years. It will become an isolated island in an expanding, darkening universe with essentially no other galaxies visible at all. Their light having been redshifted beyond detection, or their locations having moved permanently beyond our cosmic horizon. Any civilization existing in that unimaginably distant future, looking up at what remains of the night sky, would see almost nothing beyond a scattering of fading, dying stars within their own galactic remnant. There would be no evidence whatsoever that other galaxies had ever existed. No cosmic microwave background detectable anymore, because it too will have been stretched and diluted beyond any possible detection. And essentially no way to reconstruct the rich, dynamic history of the universe that we, existing today, are fortunate enough to observe directly. It's a genuinely strange thought. The relatively bright, star-filled, galaxy-rich universe we observe today isn't a permanent, steady state. It's a brief, cosmically speaking, golden age, a narrow window in the vast span of cosmic time during which stars are actively forming, galaxies remain visible to one another, and the fundamental structure and history of the universe remains observable and reconstructible through careful scientific study. Far enough into the future, the sky won't just be dark in the way we experience it tonight, scattered with countless visible points of starlight against a black backdrop. It will be dark in an almost absolute sense, nearly empty, nearly starless. Only the faint, cooling embers of long-dead stars will remain visible, if visible at all, within an isolated remnant of what was once a rich, interconnected, cosmic web of galaxies. This raises an interesting question that astronomers and physicists have genuinely considered. Would intelligent beings living in that distant future era even be able to figure out the true nature and history of the universe, the way we have? Some researchers have pointed out that if a civilization arose far enough into the future, after distant galaxies have receded beyond the observable horizon and the cosmic microwave background has faded beyond detectability, that civilization might look up at their sky and see only their own isolated galactic remnant. They would detect no evidence of cosmic expansion, because there would be no other galaxies left to measure redshift against, and they might reasonably conclude that the universe is static, unchanging, and possibly much smaller and simpler than it actually is, or ever was. In a strange way, this suggests that we exist during an unusually privileged period in cosmic history, a time when the evidence for the true scale, age, and dynamic nature of the universe is still observable, still measurable, still available to any species curious and capable enough to study it. Future civilizations, existing in a darker, more isolated universe, might never have access to the same clues we currently do. They might never be able to piece together the story of the Big Bang, cosmic expansion, or the true scale of the cosmos, simply because so much of the observable evidence will have literally moved beyond the boundaries of what they can detect. That's a humbling thought. It adds an extra layer of significance to the work being done right now, in this era, by scientists mapping the cosmic microwave background, cataloging distant galaxies, and piecing together the history of the universe, using evidence that may simply not be available to observers who come billions of years after us. Let's step back for a moment and look more closely at what actually fills the space between stars, because it's not truly empty, even though it looks that way from Earth. The space between stars within a galaxy contains what astronomers call the interstellar medium, an extremely thin mixture of gas, primarily hydrogen and helium. It also contains tiny grains of dust made of heavier elements like carbon, silicon, and oxygen, forged inside stars and scattered into space when those stars eventually shed their outer layers or explode. The density of this material is almost impossible to comprehend by everyday standards. A typical region of interstellar space might contain roughly 1 atom per cubic centimeter, compared to the air you're breathing right now, which contains something in the range of 10 to the power of 19 molecules per cubic centimeter. That's an almost inconceivably vast difference, meaning interstellar space is a far, far better vacuum than anything humans have ever created in a laboratory on Earth. Even so, across the enormous distances involved in interstellar and intergalactic space, this incredibly sparse material adds up. Dense clouds of gas and dust, called nebulae, can become thick enough to visibly block the light of stars behind them. They appear as dark patches silhouetted against the brighter background of the Milky Way when viewed from Earth. The famous dark rift that appears to split the band of the Milky Way when viewed from a dark sky location isn't actually a gap between stars. It's a dense lane of dust and gas within our own galaxy's spiral arm, blocking the light of countless stars that lie directly behind it from our perspective. This dust doesn't just block light, it also scatters and reddens it. The process is similar to why sunsets appear orange and red here on Earth, as sunlight passes through more of our atmosphere at a low angle and shorter. Bluer wavelengths get scattered away more easily than longer, redder wavelengths. Starlight, passing through interstellar dust, experiences a similar effect, becoming dimmer and redder the more dust it passes through, an effect astronomers call interstellar extinction and reddening. This is yet another factor that contributes to the darkness we observe. Though it's a relatively minor one, compared to the effects of cosmic expansion, and the finite age of the universe that we discussed earlier. Even without any interstellar dust at all, even in a perfectly transparent universe, the fundamental resolution to Olbers' paradox would still hold. The age of the universe and the expansion of space are the truly dominant factors. But dust does add texture and complexity to the sky we actually observe. It creates those dark, dust-filled lanes running through the brighter, star-dense regions of our galaxy, adding yet another layer to the interplay of light and darkness visible on a clear night. Looking more closely at exactly how astronomers measure and describe the brightness of stars helps clarify just how much of the sky's apparent darkness comes down to simple, brutal distance. Astronomers use a scale called apparent magnitude to describe how bright an object appears from Earth. Somewhat confusingly to newcomers, this scale works backward from what you might expect, where lower numbers indicate brighter objects and higher numbers indicate dimmer ones. The Sun, viewed from Earth, has an apparent magnitude of about -26.7, an extremely bright number on this scale. The brightest star in our night sky, Sirius, has an apparent magnitude of about -1.4, dramatically dimmer than the Sun, but it's still bright enough to be easily visible to the naked eye, even from a moderately light-polluted location. Under ideal, extremely dark sky conditions, human eyes can typically detect stars down to an apparent magnitude of about 6. That represents the faintest points of light the unaided human eye can pick out from a genuinely dark, unpolluted sky. Beyond that threshold, stars simply become too faint for human vision, regardless of how many of them might technically exist along any given line of sight. This magnitude scale is logarithmic, meaning each step of 5 magnitudes represents a brightness difference of exactly 100 times. That means the difference between the brightest visible stars and the faintest ones detectable by the naked eye represents a difference in brightness of many hundreds of times. When you consider that professional telescopes can detect objects with apparent magnitudes reaching into the 20s or even 30s, representing objects billions of times fainter than anything visible to human eyes, you start to appreciate just how much of the universe's actual light output remains completely hidden from ordinary human perception. Not because that light doesn't exist, but because it has been diminished by distance, by cosmic expansion, and by the physical limitations of unaided human vision, to levels far below what our eyes can register. This brightness scale also helps explain something people sometimes wonder about. Why do the planets in our own solar system, when visible in the night sky, often appear as some of the brightest points of light? Sometimes they even outshine the brightest stars, despite being vastly smaller and producing no light of their own. The answer comes down entirely to distance. Planets like Venus, Jupiter, and Mars are staggeringly close to Earth compared to even the nearest stars. They reflect sunlight across distances measured in mere millions or tens of millions of miles, rather than the trillions of miles separating us from the nearest stars. Even though a planet reflects only a tiny fraction of the sunlight that reaches it, its relative closeness to Earth means that fraction still delivers more light to our eyes than the direct, self-generated light from a star trillions of miles away. This is a small, elegant illustration of just how dramatically distance affects apparent brightness. It reinforces one of the central themes of tonight's exploration. The darkness of the night sky has far less to do with an absence of light sources throughout the universe, and far more to do with the overwhelming, almost incomprehensible distances involved. There's a subtle, observational detail that many people notice on a clear night but rarely think about, and it connects directly to everything we've covered. Stars twinkle. Planets generally do not, or at least they twinkle far less noticeably. This happens because stars, even the closest ones, are so far away that they appear as true point sources of light. They're infinitesimally small from our perspective, with essentially zero angular size as far as our eyes, and even most telescopes are concerned. As the light from these point sources passes through Earth's turbulent atmosphere, layers of air at different temperatures and densities constantly shifting and mixing, that light gets refracted slightly differently, moment to moment. This causes the apparent brightness and position of the star to fluctuate rapidly, creating the twinkling effect astronomers call scintillation. Planets, being much closer to Earth, present a small but genuine disk shape rather than a true point source, even though that disk is far too small to resolve with the naked eye. Because a planet's light effectively arrives from a slightly broader area rather than a truly infinitesimal point, atmospheric turbulence tends to average out across that slightly larger source. The result is a steadier, less noticeably twinkling appearance. This is a small but telling reminder of just how enormous the distances to even the nearest stars really are. Stars are so unimaginably far away that even our most sensitive instruments struggle to resolve them as anything other than perfect points of light. This reinforces, yet again, that the vast, overwhelming darkness of the night sky isn't a mysterious void, devoid of matter. It's the direct, visible consequence of almost incomprehensible cosmic distances. Distances so large that even enormous, blazing objects like stars shrink down to nothing more than infinitesimally small points of light by the time their glow reaches our eyes. An enormous amount of scientific groundwork had to fall into place before Olbers Paradox could finally be resolved with confidence, and the story reveals something important about how science actually progresses. For nearly a century after Olbers formally articulated the puzzle, there was no definitive answer. Scientists proposed various partial explanations. Absorption by interstellar dust, a finite universe with an actual physical boundary, even more, exotic ideas involving light, somehow losing energy over vast distances through mechanisms unrelated to cosmic expansion, an idea sometimes called tired light, which was seriously considered by some physicists in the early 20th century as an alternative to an expanding universe. The tired light hypothesis suggested that photons might simply lose energy as they traveled vast distances through space, perhaps through some unknown interaction with intervening matter or fields, which would also produce a redshift effect without requiring space itself to be expanding. This was a genuinely reasonable idea to consider at the time, and it took careful, patient, observational work to rule it out. If light really did lose energy through some kind of scattering process, as the tired light hypothesis suggested, you'd expect that scattering to also blur and distort images of distant objects, the same way scattering blurs light passing through fog or murky water. But observations of distant galaxies showed no such blurring. Their images remained sharp and well-defined, even at extreme distances, which strongly favored the alternative explanation that redshift was caused by the genuine expansion of space itself, stretching wavelengths without introducing the kind of scattering that would blur an image. Additional evidence came from detailed studies of exploding stars called supernovae, particularly a specific type called Type Ia supernovae, which reliably produce almost identical peak brightness. This makes them extremely useful as what astronomers call standard candles, objects whose true brightness is known well enough that comparing it to their apparent brightness from Earth lets you calculate distance with reasonable precision. Careful study of how the light curves, meaning how the brightness changes over time, of these supernovae behaved at different redshifts provided strong, independent confirmation that space really was expanding. This was fully consistent with genuine cosmic expansion rather than any competing tired light explanation. By the mid-20th century, and especially following the discovery of the cosmic microwave background in the 1960s, the expanding universe model, combined with a finite, roughly 14-billion-year-old cosmic history, had become overwhelmingly well supported by observational evidence. It finally provided the complete, satisfying resolution to a puzzle that had persisted in various forms for over 3 centuries. This history matters because it illustrates something valuable about how science actually works. Olbers Paradox wasn't solved by a single brilliant insight from one person. It required centuries of accumulated observation. It required competing hypotheses that had to be carefully tested and, in some cases, ruled out through patient, rigorous evidence gathering. And ultimately, it required a complete reconceptualization of what the universe fundamentally is, not a static, eternal backdrop, but a dynamic, evolving entity with its own history, its own birth, and its own ongoing expansion. There's another angle to this, one that touches on the actual geometric shape of the universe itself, a question cosmologists still investigate using increasingly precise instruments. When we talk about the universe being finite in terms of what we can observe, that's slightly different from asking whether the universe itself, in its totality, is finite or infinite in actual physical extent. These are related but distinct questions. The observable universe, the portion we can actually see and study, is definitely finite, bounded by the age of the universe and the finite speed of light. It forms a sphere around Earth with a radius of about 46 billion light-years, a number that accounts for the fact that space has continued expanding during the time light has been traveling toward us, making the current distance to the most ancient light we can detect larger than you'd calculate, by simply multiplying the age of the universe by the speed of light. But whether the universe as a whole, beyond what we can observe, is finite or truly infinite in extent, remains an open scientific question, one that current observations haven't definitively answered. Based on precise measurements of the geometry of space, primarily derived from detailed analysis of that same cosmic microwave background radiation we discussed earlier, the overall large-scale geometry of the universe appears to be very close to flat. That means parallel lines would remain parallel indefinitely, similar to the geometry you learned in school, rather than curving back on themselves the way lines do on the surface of a sphere. A perfectly flat universe could, in principle, extend infinitely in every direction, containing infinitely more galaxies and stars beyond the boundary of what we can currently observe. Alternatively, The universe could have a very slight curvature that's simply too subtle for our current instruments to detect, which would mean the universe is actually finite in overall extent, though almost certainly still vastly larger than the portion we can observe. Interestingly, even if the universe truly is infinite in its overall physical extent, containing infinitely more stars and galaxies beyond what we can ever observe, this still wouldn't reintroduce Olbers' original paradox. Here's why. Even in a genuinely infinite universe, we're still fundamentally limited by the finite age of that universe and the finite speed of light. No matter how much material exists beyond our observable horizon, none of that light has had time to reach us yet. And much of it, due to ongoing cosmic expansion, may never reach us at all, permanently trapped beyond a boundary called the cosmological event horizon that we touched on earlier. So whether the universe is finite or infinite in its ultimate physical extent turns out to be somewhat beside the point when it comes to explaining the darkness of our night sky. What matters, decisively, is that the observable universe, the only portion capable of sending us any light at all, is fundamentally finite, bounded by time and the speed of light. And expansion continues to dilute and redshift whatever light does manage to reach us across those enormous distances. This ties together the scientific explanation with a broader sense of what this puzzle actually teaches us about the nature of scientific inquiry itself. Olbers' paradox is sometimes cited by historians and philosophers of science as one of the clearest historical examples of how a seemingly simple, everyday observation can contain profound clues about the deepest nature of reality. It's as mundane and universal as noticing that the night sky is dark, a fact every single human being throughout history has directly observed. And yet those clues took centuries of careful thought, technological advancement, and accumulated evidence to fully decode. Unlike many scientific puzzles, which require specialized equipment or rare, difficult-to-observe phenomena, Olbers' paradox was available to literally every stargazer throughout human history, in every culture, on every continent. Anyone who ever looked up at a clear night sky and saw scattered points of light against overwhelming darkness was staring directly at evidence for the finite age of the universe, the expansion of space, and the vast scale of cosmic distances. That evidence simply couldn't be properly interpreted until humanity developed the mathematical tools, the observational technology, and the theoretical framework necessary to understand what that darkness was actually telling us. This is, in many ways, one of the most elegant examples in the history of science of how the universe